Welcome to today's webinar on ensuring optimal performance LC column care and troubleshooting. I'm Derek, Senior Application Chemist for Consumables from Shimadzu Asia Pacific, and I'll be your host for today. In this webinar, we are going to explore the practices for LC column handling and storage, how to identify common chromatographic problems and their root causes, and a systematic troubleshooting framework to restore column performance and strengthen method robustness. Our speaker for today is Dr. Santosh Bhardwaj. Dr. Santosh has over 21 years of experience in analytical sciences and currently serves as Manager, Expert Center at Shimadzu India Private Limited, where he is responsible for business development for the pharma and consumables market. He specialized in LC and LCMS applications across pharmaceutical, food, clinical, and chemical sector. Try. Sorry for the technical difficulty.
Dr. Derek, you're audible.
Am I audible now?
Yes, you are audible. I think, yeah, audible, yeah.
Okay. Thank you. Then I shall continue. Sorry for the technical difficulties. So let me introduce our speaker for today, Dr. Santosh Bhardwaj. Dr. Santosh has over 21 years of experience in analytical sciences and currently serves as Manager, Expert Center at Shimadzu India Private Limited, where he is responsible for business development for the pharma and consumables market. He specializes in LC and LCMS applications across pharmaceutical, food, clinical, and chemical sector, with deep expertise in LC column chemistry, including reverse phase, chelate, ion exchange, mixed mode, and specialty columns. His core strengths include column selection, method development, selectivity optimization, and troubleshooting chromatographic challenges in regulated environment. He has authored over 20 research papers and presented more than 30 posters primarily focused on chromatographic method development and validation. Joining Dr. Santosh as the Q&A panelist is myself, Derek, from Shimadzu Asia Pacific. I obtained my PhD in chemistry from Nanyang Technological University, Singapore. With over 7 years of extensive research experience, I specialize in various areas including small molecules, nucleic acids, peptides, and protein synthesis, as well as separation and purification techniques. I joined Shimadzu in 2021 as application chemist for consumables, and in this role, I'm responsible for providing technical support and application expertise for consumables in chromatography and spectroscopy. Portfolio under my care include a wide range of products such as LC and GC columns, UV-Vis cuvette, sample preparation products, sample vials, and other accessories. At the end of the webinar, we will have a Q&A session. You can use the Q&A widget to post your question. Feel free to type your questions into the Q&A chat box anytime during the webinar to submit your questions. Our speaker will try to answer as many questions as possible towards the end of the webinar. Without further ado, let's welcome Dr. Santosh. Dr. Santosh, please.
Hello, my name is Santosh Bhardwaj, working as Manager Expert Center at Shimadzu India. It is my pleasure to share some practical guidance on LC column maintenance and troubleshooting. In this session, we will focus on two key areas: the common problems faced with LC columns, and second, simple and effective preventive maintenance practices. To avoid these issues, as we all know that HPLC and UHPLC columns play a critical role in ensuring good separation quality and reliable data. Even sometimes a well-validated method can fail if the column is not properly maintained. The objective of this session is to improve consistency, compliance, and column lifetime. The question arises, why do we need to maintain HPLC column? HPLC and UHPLC columns are among the most critical and sensitive consumable in any LC system. The column is often referred to as the heart of chromatographic separation. When the condition of column deteriorates, it directly affects resolution, retention time, and peak shape. Poor column maintenance can lead to high back pressure, system suitability failures, and frequent troubleshooting. This not only compromises the data quality but also consumes valuable time and resources. By following proper column care and maintenance practices, we can ensure consistent and reliable results, maintain regulatory compliance, and significantly extend the lifetime of the column. So, what are the key do's and don'ts to keep in mind when using LC column? The best practices can be broadly divided into three stages: before column usage, during routine operation, and after column usage. By following these simple guidelines, we can maintain optimal column performance, ensure reproducible results, and extend the overall lifetime of the column. Before using LC column, especially a new one, always read the instruction manual. This step is particularly important when you are using the column for the first time. The instruction manual provides the critical information such as the maximum pressure limit, the allowed temperature range, and the recommended pH range. Understanding and following these limits, it helps prevent column damage, ensures safe, reliable, and consistent operation. During column use, it is important to set all operating limits according to the column specifications. The pressure limit is especially critical. Setting it correctly ensures that system automatically stops the run if the pressure exceeds the safe limit, thereby protecting the column from the damage. Temperature limits are usually controlled within the analytical method. However, it is still good to practice to ensure that the method temperature aligns with the column recommended specification. pH limits cannot be controlled by the instrument. Therefore, it is essential to make sure that mobile phase buffer remains within the recommended pH range. Operating outside the pH limits can lead to the bonded phase loss at lower pH or silica dissolution at high pH, both of which result in irreversible column damage. Ignoring these basic parameters is one of the most common reasons for early column failure. Understanding and following them from the beginning helps ensure good performance and a longer lifetime of the column. Proper column handling is critical for maintaining performance and extending column life. Always use compatible solvents. Ensure your samples are properly filtered and degauge the mobile phase. Also make sure the column does not dry out at any stage. Shimadzu's LC flow pilot feature helps prevent this issue. It gradually increases the flow rate during system startup, reducing pressure stress on the column by synchronizing flow increase with oven temperature stabilization. Flow pilot helps protect the column and extend its lifetime, especially for sub 2 micron columns, which are highly sensitive to the pressure shocks. The proper mobile phase preparation is very important for protecting the column and ensuring the reliable results. If the mobile phase contains particles or undissolved buffer salt, these can block the column feeds. This can lead to high back pressure and may even damage the pump. Contaminated mobile phases can also cause ghost peaks and unstable baselines, which negatively affect data quality. To avoid these problems, always filter the mobile phase using 0.45 micron or finer filters and degas it properly to remove air bubbles. Additionally, using the safety caps and suction filters helps keep solvent clean, ensuring consistent and reproducible results. Proper mobile phase preparation includes correct pH control, which is very important for column health. Traditional silica-based columns are generally stable between pH 2 to 8, while cross-linked and hybrid silica columns offer wider pH stability up to 10 or 12. Operating outside these limits can cause bonded phase loss, silica dissolution, voids, and reduced retention or selectivity. The analyst should also consider the analyte's pKa and ensure buffer has adequate capacity to maintain a stable pH throughout the run. By maintaining pH properly along with temperature control, we can significantly extend the column life and prevent the irreversible damage to column. While we talk about during the use of guard column play a critical role in protecting the analytical column. The guard column trap strongly retained sample components and matrix contaminants before these reach the main or analytical column, helping prevent damage and maintaining performance. For the best results, guard column should match the stationary phase chemistry which we are using with the analytical column. Guard columns are cost effective, easy to replace, and their use can significantly extend the life of the analytical column. Properly selected guard columns do not affect the chromatographic performance key parameters like theoretical plates, resolution, retention time. According to USP Chapter 621, guard columns can be used under defined conditions. The guard column should be no longer than 15% of the analytical column, have an equal or smaller inner diameter, and use identical packing and bonded phase. In this way, guard columns support both performance and regulatory compliance. Sample preparation is key to column performance and longevity of the column. Filtration removes particulates that can clog column pits. Filter material must be compatible with the samples and solvent, with common options including PTFE, PVDF, and nylon. Choose filter diameter based on the sample cleanliness and match pore size to column particle size. Typically 0.45 micron for 5 micron columns and not 0.22 micron for the sub 3 micron columns is preferred. Incompatible filters used sometimes can introduce extractables or adsorb analytes. Proper filtration ensures stable pressure and consistent peak shape. Column cleaning is important to maintain its performance and extend its lifetime. Common signs that a column needs a cleaning include high back pressure, changes in the retention time, and poor peak shape. Although routine column washing is different from these signs, cleaning removes contaminant from the column, especially from the front part of column as well as the inlet fit. Before starting, always check the column's pressure limits and disconnect it from the detector. Using the recommended cleaning solvents step by step helps restore the column performance almost like a new column. Column cleaning should start by flushing with additive-free mobile fish, followed by a stronger solvent if needed. Reduce the flow rate to about half of the normal during cleaning. Sequential flushing with methanol, acetonitrile, or isopropanol helps remove contaminants, while non-polar solvents like hexane or heptane can remove lipid-like impurities. Always follow the manufacturer's guideline for the use or restrictions of the solvent to be used with particular column. Reverse flushing can also help clear particulates, and the column should be re-equilibrated with mobile phase afterwards. Finally, always verify the column performance after the cleaning to ensure it is ready for the use. Column regeneration is not something to do routinely. It should be performed only when the column is nearly damaged or has lost the performance due to adsorbed contaminants. This process involves sequential flushing with solvent of increasing strength, starting with the aqueous water, followed by the acetonitrile, methanol, or then isopropanol, or non-polar solvent like hexane or heptane to remove the residues ranging from the polar to strongly hydrophobic. Use low flow rate, typically around 0.2 ml per minute, and connect the column in reverse direction while applying the flushing with the solvent. Recommended column volumes for each step should be followed properly. Ideally, it is being said with proper chemistry specific regeneration, we can significantly extend the column life and delay the need of replacement of column. After using the column, it is important to flush it with a salt-free mobile phase or a strong solvent to remove any leftover sample. Store the column in a solvent compatible with its chemistry. For example, acetonitrile or methanol with water in ratio of 65-35 volume by volume, that is 65% organic and 35% aqueous, is commonly used for reverse phase columns. Sometimes pure acetonitrile or methanol can also be used for short-term storage, but check manufacturer recommendation as some columns may dry out if stored in 100% organic solvent. You can also use same solvent that manufacturer used for shipping and mentioned in instruction manual of the manufacturer. Always tightly cap both ends of the column to prevent it from the drying out during the storage. Even with proper maintenance and care, problems can still occur. After all, the column is a consumable and has a limited lifetime. Over the time, performance can degrade due to the sample buildup, chemical stress, and physical wear. When issue arises, it is important to perform troubleshooting to identify the cause and take appropriate corrective action, ensuring reliable results and protecting your system. When troubleshooting column or system issues, there are four main approaches. Chromatographers usually use, sometimes alone, sometime in combination. First is shotgun approach. This means changing many things randomly at the same time, hoping something to work. This is the least effective method because you won't know what exactly caused the problem, making it hard to prevent it from the future. Second is historical approach. This is often the first and very important step. You review past information such as previous user, type of sample, mobile phase used, column used. This can help identify possible causes. However, it is only works well if good records or logbooks are available. Third is educated guess. This approach relies on the experience. Based on that what you observe, you link symptoms or likely causes the issue. It's faster than random changes but depends heavily on the experience of the person. Fourth is systematic approach. This is the most thorough method. You check each part of the system one by one, ruling out components until you find the root cause. Very effective, but it is time consuming. Regardless of approach you are taking, the first step to troubleshooting would always be to identify the problem, whether it is pressure issue, peak shape issue, retention time change issue, sensitivity issue. You have to first identify what is abnormal, and to do that you need to know what is normal. The best way to do is to have a reference, for example an analysis chromatogram from a standard method. This allows you to compare current results and clearly identify what has changed or gone wrong. Step in troubleshooting is to find where the problem is coming from. In an LC system, issue can happen anywhere. It may be from pump, auto sampler, column oven, detector or software. However, the most problems are usually related to the column. This is because the column is a consumable and is replaced more often than the instrument itself. So in this session, we will focus mainly on the column related issues. Some symptoms may overlap with other LC components and I will point out those as we go further. The aim is to help you troubleshoot in a more systematic and informed way. The main column issues will be covered in this session: pressure issue, peak shape issue, retention issue and selectivity issue. In general, pressure issues can be classified into three types: low or no back pressure, high back pressure, unstable or fluctuating back pressure. Ignoring pressure abnormalities can lead to the system damage or column failure, which is why monitoring pressure is a critical preventive practice. Before we look at each of these issues, it's important to understand what factors affect pressure. This helps us to know what is normal and what is abnormal. Pressure changes can be described by an equation. It may look complex, but you only need to remember how the main factors are related. Start with flow rate. Pressure is directly proportional to the flow rate. Higher flow rate gives higher back pressure. Column length, longer column produce higher back pressure. Viscosity is also directly proportional to the pressure. More viscous mobile phase require more force to move through the column, resulting in higher back pressure. One key point consider while studying the pressure issues: in isostatic methods, the mobile phase viscosity stays constant, so pressure should remain stable. In gradient methods, mobile phase composition keep on changing, so viscosity and pressure will vary accordingly. So low or no back pressure usually happens sometime when there is not enough mobile phase in the reservoir. This often occurs when mobile phase is used up without the user noticing. So always make sure you have enough mobile phase for the entire analysis before starting the sequence. More commonly, however, low or no back pressure is caused by leak or loose connections in the system. Fortunately, these problems are usually easy to fix. Following steps need to be followed for the troubleshooting of low back pressure. Check the mobile phase level before starting your run. If available, you can use Shimadzu LC mobile phase monitoring option, which tracks the mobile phase level and alerts you when it is running low. Inspect the system for leaks along with the mobile phase flow path. One of the most common places for leaks is tubing connections. The column inlet is frequent source for the leaks, especially in the column where it is installed recently and not tightened properly, or if connections was made incorrectly. Using an incorrect or incompatible fitting can also cause leaks, so always ensure you use recommended component. By following these checks, you can usually identify and fix low or no back pressure issues very quickly. Connector fitting play a critical role in maintaining flow integrity. Inappropriate fittings can cause leaks or dead volume, which can affect system performance. These different types of column fittings and they differ in pressure rating. Our ultra high pressure fitting has a pressure rating of 172 bar, suitable for all HPLC specifications as applications. Our finger tight high pressure fittings has a pressure rating of 827 bar, suitable for HPLC applications. A tightening tool is also available to help properly tighten the finger tight high back pressure fitting. So always ensure you are using fittings with the appropriate pressure rating for your application. If you are using guard columns, keep in mind that connectors on the guard column are also a common location for leaks. High back pressure is usually observed when there is a flow restriction somewhere in the system. The most common cause is clogging inside the column or guard column, often caused by the particles from the sample or mobile phase that accumulate at the column inlet frit. In some cases, buffer salts can precipitate and block the flow path. Particles in the sample can also block the inlet filter, leading to the increased pressure. To understand this, let's look at the column design. A column is essentially a hollow metal tube filled with silica particles. At both ends, there are filter frits that keep the silica packed inside and allow mobile phase to pass through. When particles are present in the sample, they can trap the inlet frit. Over the time, this causes clogging, which results in high back pressure. In the image shown, inlet frit on the left side is from the column with a high back pressure issue. You can see a visible discoloration compared to the clean frit on the right side. This build-up is likely cause the increased pressure. This is why we strongly recommend filtering the samples before injection. Particles can come from the mobile phase, especially when an inappropriate solvent grade is used or the mobile phase is not filtered. Another possible cause is microbial growth in aqueous mobile phases. To minimize this risk, always use appropriate grade solvents and filter your mobile phase, especially when buffers are involved. Some contaminants such as proteins can bind strongly to silica particles. Over time, this buildup can also increase column pressure. Proper sample preparation can greatly reduce this problem. Finally, improper column use such as operating above the recommended pressure limit can damage the silica packing and lead to the higher pressure. All of these factors together can contribute to high back pressure in the LC system. If you are experiencing high back pressure issue and have confirmed that the column is the cause, there are several remedies that can help extend the life of the column. The first step is to flush the column to remove contaminants. Use strong solvents without buffers or salts, as these are more effective for cleaning. Sequential flushing with different solvents can further improve cleaning efficiency. During flushing, reduce the flow rate to avoid the pressure spikes, typically around 0.2 ml per minute. Reverse flushing may help clear blockages at inlet frit, but this should be done only if permitted by the column manufacturer. During cleaning, always disconnect the detector to prevent the contamination or potential damage. If the pressure remains high even after thorough cleaning, it may indicate the permanent damage and column replacement may be necessary. Prevention is always better than fixing problem later. Here are some key practices to help avoid pressure issue with your LC column. Filter samples and mobile phases regularly to prevent particulate buildup. Always operate within the column's recommended pressure and pH limits. Prepare sample carefully to minimize the particles and contamination. Use guard columns to protect the column inlet frit clogging. Perform regular system maintenance to prevent residue buildup. Avoid sudden pressure changes in flow rate which can stress the column. Monitor pressure trends so you can identify and address the potential problems early. By following these preventive steps, you can maintain stable pressure, protect your column, and ensure reliable performance. Peak shape is an important indicator of the health of your column and overall LC system. Common peak shape problems include splitting, tailing, fronting, broadening, host peaks and changes in the retention time as well. These issues often have multiple possible causes such as column contamination, problems with the guard column, overloading the column, extra column dead volume. By carefully observing and understanding peak shapes, you can quickly identify underlying problems and take the appropriate corrective action before they affect data quality. Peak splitting in HPLC usually points to a problem with the column or how the sample was loaded. The most common cause is coelution, where the similar compounds are not fully separated. Another frequent cause is column overloading due to a high injection volume or high sample concentration. This can often be corrected by reducing the injection volume or diluting the sample. A contaminated guard column can also disturb the flow and lead to peak splitting. In many cases, simply replacing by the guard column resolves the issue. If the analytical column itself is contaminated, it may require cleaning or replacement. Finally, pressure shocks, crystallization, or improper storage can also create voids in the column, which may result in persistent split peaks. Sample diluent incompatibility is a common but often overlooked cause of the split peak. If the diluent is stronger than the mobile phase, especially for early eluting compounds, poor focusing can occur at the column inlet, leading to the distorted or splitted peak. To remove this or to prevent this, always match the diluent strength and pH as closely as possible to the mobile phase and consider reducing the injection volume. Peak splitting can also be caused by the void at the column inlet, which can disrupt normal flow. Such voids are often created by mechanical stress or pressure shocks applied to the column. In more severe cases, such as bed collapse caused by the operation at high pH, the damage is irreversible and column replacement may be necessary. Peak telling and broadening usually occurs when the column is overloaded, meaning too much analyte is introduced relative to the column's capacity. This leads to the nonlinear adsorption, which results in asymmetric and wider peak. Detector saturation or column contamination can further worsen this shape. Over the time, column aging and loss of the bonded phase can also contribute to increased telling and higher back pressure. To maintain the sharp and consistent peak, it is important to follow proper maintenance practices and replace the column at the appropriate time. The secondary interaction are a common cause of peak telling, especially for basic compounds. Free selenol groups or silica surfaces or metal surfaces in the flow path can interact with positively charged analytes, leading to the telling peaks. To reduce these interactions, using end-capped column and metal-free hardware can be very effective. Adjusting the mobile phase pH or using hybrid silica columns can also significantly improve the peak shape. Ion pairing reagents may also help in some cases, but they can be complicate the method robustness and should be used with the caution. Ultimately, understanding the chemistry of the analyte and selecting the appropriate column and conditions are key to minimize secondary interactions and achieving good peak shape. The extra column dead volume is a common cause of peak shape or peak broadening. It occurs when there is a long or wide tubing or sometimes loose connections or large detector flow cell, all of which increase the band dispersion before reaching to the detector. To minimize this effect, use short or narrower tubings. Ensure that all connections are properly tightened, firm but not over tightened, especially at the column outlet. Dead volume issues are more pronounced in the UHPLC system as they are much more sensitive to even a small increase in extra column volume. Fronting peaks usually observed when column is overloaded. So column overloading is issue for all type of peak shapes. Too much sample at column inlet saturate the stationary phase. This can be fixed by injecting less sample, diluting it, or using a higher capacity or higher surface area column. Fronting can also caused by the incorrect mobile phase pH. Adjusting the pH and making sure sample is in a single form helps prevent this. Fronting shows non-linear adsorption and solving the root cause will restore the peak shape. Ghost peaks are unexpected peaks that are not related to your sample injected to the system. They often occur when sample matrix component adsorb onto the system or column and then elute later during the subsequent runs. Ghost peaks can also appear due to mobile phase contamination, contamination from solvent bottles, LC tubing, or even laboratory environment can also generate ghost peaks. To minimize ghost peaks, it is important to perform proper system cleaning, use a optimized needle wash, and allow sufficient gradient wash and equilibrate the column between runs. Carryover peaks also the same sometime understood as ghost peaks. These are smaller and most commonly caused by the insufficient needle washing. Carryover can be eliminated by using an appropriate rinsing solvent and optimizing the method parameter, such as rinsing before and after the sample aspiration, ensuring an adequate needle dip time at rinse port. Carryover is often occurred due to the injector or needle. By carefully controlling these factors, both ghost peaks and carryover can be effectively reduced or eliminated. To prevent ghost peaks from system, regular LC maintenance of system and flushing of mobile phase lines reduce the residual buildup in the system. Use of strong wash solvent, perform sample cleanup to remove adsorbed compound, filtering the samples, stop particulates from the reaching the column, while guard column trap the contaminant before they enter to the analytical column. A ghost trap removes trace organic contaminant from the mobile phase before they reach to the column. This also helps to improve the baseline stability and reproducibility, especially in gradient methods. It is installed after the gradient mixer and before the injector, ensures contaminant from the mobile phase are removed and do not reach the detection system. Ghost traps are available in HPLC and UHPLC compatible formats to match system pressure requirement and their use significantly. With a clean baseline and absence of ghost peaks along with reliable peaks integration, HPLC analysis become more consistent and reproducible. The ghost trap columns play a critical role in achieving this by removing trace contaminants and stabilizing the system. Overall, it improves data quality and ensures accurate and confident quantification in HPLC analysis. Changes in retention time often signal the system or column issues. The most common issue include changes in the mobile phase composition and variation in the flow rate, which directly affect how the analyte move through the column. Column contamination or aging can also alter the analyte's interaction, reducing the selectivity and shifting the retention times. In addition, temperature fluctuation can impact the retention, especially in the method sensitive to the thermal changes. To address these issues, preparing fresh mobile phase, washing the column and replacing the aged column help restore stability. Maintaining consistent and equilibrium or monitoring retention time trends can prevent unexpected retention shifts and ensure reliable and reproducible results. In summary, common HPLC issues include high pressure, poor peak shape, and changes in retention time. Many of these problems arises from the system or mobile phase contamination, highlighting the importance of proper maintenance and care. Protecting your column not only helps maintain performance and data reliability, but also extend the column lifetime and reduces the system downtime, making your analysis more efficient and reproducible. Let's conclude with troubleshooting best practices and key takeaways from this session. Effective troubleshooting follows simple discipline rules. The rule of one, change only one parameter at a time to avoid misinterpretation. The rule of two, ensure the issue is reproducible. A problem only exists if it occurs at least twice. If a part is changed or replaced and the problem persists, reuse the original part unless it is worn or expired. Discard bad parts to avoid future confusion. Documentation and maintenance logs provide traceability and historical insights. HPLC column care is key to reliable chromatography. Most problems can be prevented with proper handling, maintenance, and understanding of the column chemistry as well as their limits. Guard columns, filtration and preventive practices protect the column and extend its life. Systematic troubleshooting and good documentation ensure data integrity, regulatory compliance, and consistent high quality results. Well maintained columns save time, reduce cost, and form the foundation of the robust analytical science. Thank you for your kind attention. We hope this session has clarified how the right consumables, especially columns, improve HPLC performance and data quality. For any question or application support, please feel free to contact us using the details on the screen. We look forward to supporting your analytical needs. Thank you.
Thank you, Dr. Santosh, for the wonderful presentation. We hope that you have we hope that you have a better understanding of HPLC column care and troubleshooting. We'll now move on to the Q&A session. So let us welcome back Dr. Santosh and we will answer your questions. Dr. Santosh.
Yeah, thank you, Dr. Derek. So now we can take up the Q&A session.
Yeah, we see some questions coming in. So please feel free to send in more questions so that we can answer them today. Okay, so the first question that I see, after use of column, it should be stored in which solution? So I think I can take this question and maybe Dr. Santosh, if you have anything to add on, you can add on after this. So when after using of your columns, the solution that you're supposed to store can differ depending on which columns that you are using. So it is always the best for you to refer to the instruction manual that accompanies the column. So most instruction manual for columns will indicate which solution that you are supposed to store. But as a rule of guideline, never store your column in extreme pH condition, even though it is stated that it has a pH stability within the range. So it is best to keep it at more of a neutral region so that it does not really damage your silica. Second is that always do not store your column containing salt buffer in the solution because salt buffer can tend to precipitate and it can cause damage to the column. So Dr. Santosh, is there anything that you would like to add on?
Yeah, thank you, Dr. Derek, for a brief answer. And my answer, it's a very good question, first of all. So as I mentioned in my presentation as well, the storing column is very important to extend the life of the column. So while if we talk about the reverse phase column, C18, C8, or phenyl, or even helix columns, the best storage solvent we consider the combination of aqueous and organic. If we are using 100% aqueous, there are chances of algae formation, and we are using 100% organic, there are chances of drying out of the column. So best composition that manufacturers recommend is 65% organic. Either you can use acetonitrile or methanol and 35% water. Sometimes for short-term storage, you can also consider to store in methanol or acetonitrile 100% as well, but it's for 1 or 2 days only. Long-term storage, it should be aqueous and organic combination. I hope we could clarify your question. If anything else, then we can connect further as well.
Thank you, Dr. Santosh. So we'll move on to the next question. The question is, what should be the cleaning solution? Maybe Dr. Santosh, you can take this question.
Yeah, thank you, Dr. Derek. Of course, I can take. Regarding the cleaning, it always depends what was the previous analysis be performed on the column. If suppose it's like a phosphate buffer, then we generally washing is performed by the using minus buffer, that is the aqueous and organic, means without buffer we can flush. And sometime if buffer high concentration is being used, in that case we generally prefer to use 100% water for less time only, not more than 5-10 column volume. If it is more time, it may dissolve the silica, hydrolyze the silica part. So better you can use 90% water and 10% organic. If high concentration or high volume of high composition buffer used, otherwise best practice is to minus buffer from the mobile phase. You can flush the column, and later on, if you suppose like your samples are like having high matrix effect and sometime high organic is required, in that case 100% methanol washing can also be given. So it depends case to case. Ideally salt free mobile phase is okay for the washing.
Thank you, Dr. Santosh. We'll move on to the next question. After use, what should be washing sequence and time of washing? So the instruction for washing, I believe most of the case in most of the column, the instruction manual will have a certain guideline. So it is good, or you should always consult the instruction manual as the first initial understanding. And I also believe that Dr. Santosh has briefly went through this information during his presentation. So maybe if Dr. Santosh has anything that he can add on, please feel free. Dr. Santosh.
Yeah, thank you, Dr. Derek. Although there is a sequence that I mentioned in my slides as well, while using the mobile phase, means for reverse phase column, if you wanted to consider for a strong wash, then sequence is miscibility is always considered. If you are using methanol water, and then we suppose we sometime mention like for removing the some non-polar or polar impurities or some lipid type of impurity, we recommend washing by the IPA, isopropanol, or then followed by the heptane or hexane. But even like while we use heptane or hexane washing, then we should consider to again use IPA to remove the hexane or heptane. If you use methanol water after hexane heptane, then immiscibility issue will come and column may damage. So the sequence is very well mentioned in my slides. Even you can refer the instruction manual of the Syzygy columns, where this sequence is also mentioned. And I hope this clarify your question. If anything else, we can connect one-on-one later on. I hope you got our contact details from the screen.
Thank you, Dr. Santosh. So we'll move on to the next question. We have time for a couple more questions. The next question is, any calculation formula for column wash? So I believe you are referring to the column volume that we are mentioning. The most simplest calculation would be the cylinder formula for the volume of the cylinder. So if you have a 4.6 by 250, then you will have the pi times radius squared times the length of your column. But that is only the total volume of that column, but we did not factor in whatever that is being packed in it. So depending on if it is a superficially porous particle or fully porous particle, we usually would have another fraction, another factor that will be added to it or multiplied to it, so that we can have the correct column volume. But if you do not want to add in this factor, it is also okay for us to keep to the column volume of typical cylinder formula. So is there anything that Dr. Santosh would like to add on to this?
Yeah, Dr. Derek, thank you. A very brief answer, but in order to align that, I'll just repeat or just mention few things. As you mentioned, column is in cylindrical shape. So the formula of cylinder, I think we all are aware, it's a very basic science. The formula is pi r square h, where the pi value is 22/7 or 3.14. And radius, of course, the internal ID divided by 2 is radius, and then ultimately length. So if you are using these dimensions in millimeter, you're going to calculate the column volume in microliter. If you're using in centimeter, you are getting in the ml. But of course, as mentioned correctly by Dr. Derek, this column is not empty. It is filled with the silica and packing material. So the factor of porosity, that is also well mentioned in the instruction manual. So you can get the exact column volume with the packing material, and that volume is used either for the strong washing or column regeneration. So it's a very good question indeed. I appreciate. If you're not knowing the column volume of your column, then you cannot predict the column equilibrium time as well as the washing time. So thank you for this good question to bringing in the knowledge of all the participants. I think it will be helpful. Thank you, Dr. Eric. Yeah.
Thank you, Dr. Santosh. We'll move on to the next questions. So sometimes peaks goes below the baseline. So maybe Dr. Santosh has the answer for this. Dr. Santosh.
Yeah. Yeah. So yeah, Mr. Mahendra, very good question again. So the baseline goes negative or sometimes negative, positive both. So it like two times it may happen. One is at the unreturned time, that is the first peak coming initially at 1.5 or 2.5 minutes, depending on the length of the column. That is known as unreturned peak, and then can happen by the deviation in the absorbance of mobile phase and diluent, or sometimes with the mobile phase absorbance itself, it can go positive and negative. So unreturned peak is okay, and it is directly correlated with the column volume. So suppose column volume is 2.5 ml and a peak observed at 2.5 minutes, so we can also consider this is column volume. If suppose any peak coming negative after analyte peak or in between of the analyte peaks, specifically for the UV or PD detector. In RI detector, it's a common phenomena, since by the changing the RI value, it may go anytime. But in UV or PDA, if something going negative, then it considered any impurity or any contaminant from the mobile phase present, which absorbance of that content or analyte is lower than the your mobile phase. In that case only, it may observe negative. Otherwise, negative peaks generally don't observed in the universal detectors like UV or PDA. Hope I could answer your query. If anything else, Dr. Derek, if you like to add something, thank you for that.
Yeah, thank you, Dr. Santosh. I think you have explained it really well. I think we can move on to the next questions. We have a couple of more minutes to go, and we can see that there are more questions coming in. So we'll try to answer as many as possible. So the next questions we have is, can we run the column in opposite direction as indicated in the column? So I think we get these questions quite a lot of time, and most of the time we will answer you that it is always not recommended for you to run your analysis in the reverse direction, because in the manufacturing of the columns, it is packed in a single direction. So running it in the opposite direction gives a chance that it can disturb the packing of the bed, and it may create some problems during your analysis. But if, as you have aware during Dr. Santosh's presentation, in some cases when we are doing troubleshooting where you have high pressure and we suspect that there are something clogged in the inlet of your column, we will recommend for you to run in reverse direction in hope that these particles that clog your column can be dislodged. So in usual application, we do not recommend you running in opposite direction, only when during measures that you need to do certain troubleshooting, then you may be able, you may need to run it in opposite direction. So is there anything that Dr. Santosh would like to add on?
Yeah, thank you, Dr. Derek. Yeah, of course, you clarified the query. I just wanted to add, since in India, it's very common to use the column in reverse direction while it is not performing in the right direction. Maybe due to sometimes a higher back pressure from the inlet side, right direction, and maybe sometime the peak switch. So of course, no manufacturers recommend the using the column in reverse directions. If so, no direction being included in the column. So it is not recommended. Even if you use column in reverse direction, ultimately the column life being degraded. So column will degrade faster as compared to using the column in right direction. So better to try to wash the column to remove any accumulation of the particulates on the inlet frit or inlet packing material. So just in reverse direction, a lower flow rate, typically 0.2 ml or 0.3 ml, not more than that. Otherwise, end packing may get affected and packing material also get affected. So generally don't recommend, but somehow if analysis requirement and analysis is important, then of course we cannot restrict, but we can guide to try to use the column in right direction and having the more life of the column.
Thank you, Dr. Santosh. Maybe we can move on to the next question. We see a similar question, how to calculate the column volume. So I think we have already answered this question. The next question is the hexane solvent suitable for reverse phase columns? I think Dr. Santosh, would you be able to take this question?
Yeah. So hexane is not compatible for the reverse phase column, although certain amount can only pass through. That is even after using the IPA, that is a replacement solvents. So hexane not suitable for the like general C8, C18 columns. It can be used only for removing the some polar or non-polar impurities or lipid type of impurity from the column.
Okay. Thank you, Dr. Santosh. We'll take maybe one more questions. Time is running short. The next question we have, in your column washing process, you told to use IPA, but is it safe? If safe, then what will be the composition? I think IPA has been used quite commonly in reverse phase analysis. It is more or less an alternative to ethanol. So yes, IPA is safe to be used in reverse phase HPLC. Yeah. Regarding what composition, I think in terms of IPA, the most problematic about IPA is the high viscosity that creates higher back pressure. But other than that, I believe going up to higher compositions like 100% IPA is still possible. Is there anything that Dr. Santosh would like to answer or add on to this?
No, Dr. Eric, I think you covered the subject. Yeah, thank you.
Yeah, I think it is time is running short. Maybe we have time for one last questions before we end this session. I'm using phosphate buffer and washing method is 10% acetonitrile in initial, and in 2 hours it goes to 90% acetonitrile in linear gradient. So I think you are asking about the washing step. When you increase your organic solvent to a high percentage, you need to take care of precipitation that may occur during this changing into a high organic concentration. So what is suitable, I may not be able to answer directly right now because we do not have the information of the concentration of your phosphate buffer. So it depends in a lot of factors, including how much phosphate you have in your aqueous space and also the temperature of your column. So you will determine whether the solubility of your phosphate within the organic phase. Yeah. Is there anything that Dr. Santosh would like to add on?
Yeah, Dr. Eric, I think you covered the subject. Since if we don't have the information on the mobile phase composition and buffer concentration, it's hard to comment like even the 90% acetonitrile is safe while even in gradient.
Thank you, Dr. Santosh. I think our time is already up, so we shall end this session. Thank you once again for Dr. Santosh. I'm sure our audience has learned a lot from your sharing today. Thank you.
I just would like to add, sorry, Dr. Derek, to mentioning. I would like to just to add to participant. We will take up the questions based on your email IDs. We will share the answers on your email IDs, and we look forward to your feedback or if anything required from our side. So I had shared the contact details on my screen. Hope you noted down, and you can contact us, and we will further be in connect. Thank you.
Thank you, Dr. Santosh. So to those who have posted your question that weren't answered because of time, don't worry, we will be responding to you via email. And with that, we hope you have enjoyed today's session and have a great day. We look forward to having you again. Thank you.